Very glad to have Dr. Indrajit Paul. He has earned his MSc from IIT Kanpur in 2014. His PhD is from University of Siegen in Germany, where he focused research on artificial molecular mechanics machines. After finishing his doctoral studies, he joined Signature Discovery, a pharmaceutical company based in the UK, as a senior scientist. Since November 22, Dr. Indrajit has been conducting postdoctoral research in Miguel Garcia Garibay's group at University of California, Los Angeles, focusing on solid-state photochemistry and quantum information science. So Dr. Indrajit talk is titled Triple Synthesized Quantum Amplification Crystalline Solids. So with these few words, I invite Dr. Indrajit to deliver his talk. Dr. Indrajit, over to you.
Can you hear me? Or like I can see people around, but
Yeah.
a lot of voices are coming.
Yeah, we are able to hear you, Dr. Indrajit.
Okay, so I can start. Okay, good morning, everyone, and thank you so much for the kind introduction. And before going to my talk, I would like to thank, first of all, MIT, the Department of Chemistry, all the conveners, and particularly all the eminent speakers, attendees, and participants. And it's really nice symposium. I haven't had like much chances to listen up all the speakers of the US and India, huge time difference. But I would like to listen more about it when I get the recordings. Okay, let's go into the talk first. Okay, so today I'll be talking about triplet sensitized quantum amplification in the crystalline solid that I'm doing in UCLA under the supervision of Professor Miguel Garcia Garibay. So we are mostly interested in the solid state chemistry, solid state reactions. So far, we have listened up a lot of things that has been done in solutions, like reaction asymmetric synthesis in the solutions. But very few groups are actually doing the reaction in the solid state. So we are one of them actually interested to do reaction in the solid state and also like spin dynamics in the solid state. So before going to my original talk, I would like to give a short introduction of it. So if you look at the literature, you will find like two kinds of reaction. So one of the reaction that is known as the photochemical non-adiabatic reaction. So that's like a very common and like a normal reaction. So most of the reaction goes via this pathway. So I can explain it well. So if you take the substrate and heat with the light, so it will go to the singlet excited state, and then it crosses the intersystem crossing and going to the triplet excited state. And then it's going back to the product, right? So in this case, the absorbed energy is actually dissipated by forming the product or by other mechanism. Or you can just heat the sensitizer and going to the excited state. Now you're populating the triplet state of the sensitizer. That sensitizer actually close energy to the substrate triplet state, and then it's going back to the product. In all the cases, the energy that is absorbed by the starting material is actually dissipated through forming the product. And in that case, the quantum is actually varies from 0 to 1. You cannot exceed more than 1. But if you look at the other reaction, that is called photochemical adiabatic reaction. And in this case, if the triplet substrate energy is transferred to the triplet product, and if this energy difference is actually greater than this energy difference, then you have a chance to transfer the energy from the product to the another one substrate. Then you have a chain reaction. In more elaborate way, I can explain to the energetics. So we have the sensitizer, if you look at, so we are populating the triplet set of the sensitizer that actually transferred to the starting material, and that energy will transfer to the product, and this product energy, if you look at, transfer to the new starting material. And in this way, you have a chain reaction. So you are just giving single photon, single quanta, and you are having multiple reactions in the system, right? Now, we have chosen a very specific system where we can use this quantum chain reaction in the adiabatic pathway. So this is the duobenzene, that is one of the isomer of the benzene. Since this duobenzene, you can see very strained and very reactive molecule it is. So we have to take the sensitizer. That sensitizer will be absorbed by the light, and their triplet sensitizer will transfer the energy to the duobenzene, and that will form triplet Huckel benzene. This triplet Huckel benzene will transfer to the another one duobenzene in the system, and in that way you have the product Huckel benzene and another one triplet Huckel benzene, and in that way you have a chain reaction. So this is the energetics we have calculated. You can see by the energetics that this particular energy gap, like single triplet energy gap from the starting material, is around 68 kilocalorie. But if you look at the product, this energy is actually 84 kilocalories. So this is very important that these particular energies should be greater than the energy of the starting material. And in that way, you have a chain reaction. Now the question is whether you can do this kind of adiabatic chain reaction in the solution as well as in solid. So in solution, there is a problem that in solution you have starting material, you have reagents, but you have also the solvents. This solvent molecule can interact with the starting material, all sort of like a mechanism can happen, and then you have a dissipation of the energy. You cannot just transfer the energy more efficient way to the next starting material to have the efficient reaction. In that perspective, we thought, okay, let's do this kind of reaction in the solid state. So we have thought of doing this reaction in solid state by exciton-enabled quantum chain. So in this case, we have a solid block, and we have a lot of molecules that are like nicely organized and periodic. So we just hit one of the molecule by the light, and it forms the exciton. And this exciton will hop in the crystals, and you have a quantum chain process. So we need to do everything in the solid state, and for that, the compound should be very solid and nicely organized. And in that way, we first synthesize the first generation duobenzene. In this case, you can see the first duobenzene has been synthesized with a carboxylate, dimethyl dicarboxylate. This compound, unfortunately, is not solid. It is actually colorless oil. We cannot do any experiment with that. Now we hydrolyze this dicarboxylate to form dicarboxylic acid, and we found that this compound is very crystalline. We obtained the X-ray structure. By looking at the X-ray structure, you can see this particular compound is actually forming the very linear, like a chain compound. So in that way, if you just hit one of the duobenzene, it forms hydrobenzene, and it transfers energy very efficiently to the next duobenzene, since the two duobenzenes are very close to each other. So afterwards, we have synthesized a compound with the sensitizer. As I talked about, we need to install the sensitizer to introduce the greater quantum yield. We have also calculated the quantum yield for the dicarboxylic acid. This quantum chain is not very high. It's around like 10 to 12. So it's not much. So therefore, we have introduced the sensitizer in the duobenzene. This compound, we can see this is the sensitizer. We have obtained the crystal structure. In the crystal structure, we can see like two duobenzenes are very close to each other. It's around 5.1 angstrom, the distance is. So if you just hit the benzophenone with the light, it transfers the energy to the duobenzene, and then this duobenzene will efficiently transfer to the next duobenzene, and in this way, you have a chain reaction. Now the question is, how do you do this reaction? So first we grow the crystal, we put it in the light source under the microscope, and we heat the crystals with the light, and we see what happens. Initially, we have found that the crystals actually gets melted after heating the light, because this light wavelength is much, much shorter than the crystal size. And because of that, the crystal is not able to like react in presence of the light. It's just melting from the surface. You have the reaction on the surface. So this is not the like a proper way to do the reaction. So in that way, we need to find some other method, right? In the left-hand side, you can see here a lot of like crystals. We can see like it's heated by the light and it's scattered back. It doesn't like penetrate to react with all molecules. So we thought, okay, let's like make the crystals much smaller. So this is like a micron scale crystals. Now we need to make nanoscale crystals. So how we can do that? So we just take the compound, dissolve in ethanol and methanol, and then just put it in the water, and we can see the milky suspension. And this suspension is actually the crystalline suspension. This suspension, we put it in the SCM, we can see like block-shaped nice crystals, and this crystal size is actually matches with the light wavelength. And since it's matching with the light wavelengths, the light can nicely penetrate to the crystals, and you have like very nice reaction. So now we solve the problem that how we do the reaction. Now, by using the nanocrystalline suspension, so first we have taken this compound, we use 310 nanometer of the light, 30 minutes with the nanocrystalline suspension, we got this product, and we calculated the quantum yield in the nanocrystalline suspension, it is 120. Means we are giving one photon, one quanta, we are getting 120 reactions. But when you do this kind of reaction in the polycrystalline suspension, we get 300 quantum yield. So in this case, the problem was this compound was not very crystalline, it was not very solid. So we have to use a different technique called polycrystalline suspension. For that, we just have to take the compound, grind it in the mortar pestle, then you just suspend in water and then sonicate it. You can really see the suspension, and that suspension you have to use for the reaction. And we really can achieve 300 as a quantum yield. And in this particular compound also, we can see in the solution also very high quantum yield. But for that, we really need to have very high concentration. As I said before, once you have a solvent, the solvent will interact with the light, and it will actually create problems. In that way, you have to increase very high concentration so that you can minimize the solvent and solvent molecule interactions. So in the left hand side, you can see the triplet lifetime we have calculated in the solution 1.9 microsecond. But in this case, as I said, this compound is not very crystalline. We are not able to get the lifetime for the solid. So it is actually in the solution. Then we thought, okay, how we can improve the crystallinity of the compound. So then we brought this particular sensitizer, and we have already this dicarboxylic acid. We just mix it, we grow the crystals. You can see this particular compound is very crystalline because it's a salt. So this is the crystal we obtain, the block shape crystal. We can see like all the components are nicely crystalline. We got the crystal structure. We also have the px30 validation that the bulk crystal, nanocrystalline suspense are in the same phase. There is no other phase, no other components, and no other complexation. So all the components are in the same phase. So we have done the laser flash photolysis to see the lifetime for this particular compound. So this compound lifetime in the solid state, we got almost like a microsecond lifetime. So this is the first time we got the solid state lifetime. And by looking at the lifetime, we can easily conclude that the quantum yield will be very high. We have calculated the quantum yield for this particular compound. It's around like 450 quantum yield. This means one quanta can give like 450 events. So this is the equation we follow for measurements of the quantum yield. And this is the standard setup we follow to measure the quantum yield. You can see at the back we have the mercury lamp. So the mercury lamp has the full spectrum like 200 to 800 nanometer. And this is a little box. You can see the box has been made. And this little window is basically a glass plate with 340 nanometer of the filter, so that we can just cut off the light like below 340 nanometer. The two tubes are there. The two tubes have, one has the actinometer, means standard, another one has the analyte. This standard we have used, this has been published before, and with quantum yield of 300. So in that way, we can just do the experiment with a certain time. Then we dissolve this compound in some solvent, check NMR, and we get the number of molecules as reacted, and we just put it in the equation, we get the quantum yield. In that way, we always measure the quantum yield. Okay, let's think about something else. Like we have already said that once you have a sensitizer, you can amplify the reaction, right? But once you have like no sensitizer, how you can amplify the quantum chain? So for that, we first grow the crystals where we don't have any sensitizer. In this case, we can see like it's forming very nice crystals. We obtain the crystal structure. We have measured the quantum yield. So quantum yield is around 22. So by looking at the crystals, we thought, okay, we have seen these kind of crystals before. So this compound with sensitizer and this particular compound is very similar, the structure. So we thought, okay, let's merge together in the mercury and see what happens. Once you just merge it, you will see it's almost 95% of the similarity. Then we look back the literature. We search that once the two compound has the similarity more than 85%, you can really form the solid solution. Means you can really make a mixed crystals. So how we make the mixed crystals? So we just take a crystals where we have like a very tiny amount of the sensitizer induced duobenzene. The rest of all duobenzene has no sensitizer, right? So then you can heat the sensitizer with the light. Then you can make the Huckel benzene with a very high yield, and then you just transfer the energy to the next duobenzene, because there is no other way to release the heat, this energy to other way. So it has to transfer the next duobenzene. So after formation of the next Huckel benzene with a very high yield, it just transfer to the next duobenzene again, and in that way you have many reactions with a single photon in the crystal by forming the solid solution or mixed crystals. Then we optimize the mixed crystal formation. So once you take the host and guest with a specific percentage, you can really make the mixed crystals. So you just have to take 95 host and 5% of guest. You can really make the same amount of the mixed crystals. But if you just increase this particular amount, you need to use little more. So you can see like once you want to make like 90:10 ratio of the mixed crystal, you have to mix 80:20. But if you want to increase the percentage of doping, you have to use more and more. But we are not able to see any kind of mixed crystal formation beyond 10%. So this is the limit we got, and you can see in this particular plot, we can really achieve 0.1% of the mixed crystal. So the maximum loading is 10%, minimum loading is 0.1%. So after reaching out this particular mixed crystal formation, we thought, okay, let's look at some kind of like pictures of the crystals, see how it looks. So the right hand side, this picture, you can just follow carefully. So this is the crystals for the host, for the guest. block shape crystals are there. For the host, you can see tiny crystals are there. Once you mix these two crystals to grow again, you can see very small crystals are forming. It's not possible even to measure the crystals. But if you want to increase the doping, then you have to increase the amount of gas there, right? So in this case, you can see there is no mixed crystal formation. Rather, it just formed two different phases. You can see the block shape gas and was it just separated. We have used the solid state 13C NMR measurements to clarify everything. You can see the host 13C NMR, this is the peak is around like 200 ppm. So when you have like 5% mixed crystal, you can see this peak has been shifted a little bit in the uphill region. Now when you have a 10% mixed crystal, you can see this peak, the peak is actually prominent. Now if you increase the percentage, there is no mixed crystal formation. You can see like a separate phase. And this peak actually matching here means there was no mixed crystal. We tried to get the quantum yield, and the quantum yield was very, very less because there was no mixed crystal. Now this is the overall quantum chain reactions profile. You can see when you have like a sensitizer, you have 450 quantum yield. When there is no sensitizer, we have 22 quantum yield. But when you have 0.1% of sensitizer, as I said, we have 517 quantum yield. Whereas when you have 10% of sensitizer, we have 455. Now the obvious question is why when you have like less loading, you have more quantum yield. So we have postulated that when you have greater amount of sensitizer, that sensitizer will actually self-quench in the solid, and because of that, we have less quantum yield. So more quenching, it will create the less quantum yield. So since we have a 0.1% of sensitizer, there is no quenching in the excited state, and then you have a very high quantum yield as well, 517. So after obtaining this quantum chain system, we thought, okay, let's think about beyond this particular dual benzene and quantum chain, how we can accelerate the other reaction in the crystals. So recently we have published this work. So here we try to grow the crystals where we have two different units will be there. So the first unit will have the dual benzene, the second unit we have dipyridine ethylene unit. So you can really make nice crystals of these two particular components. And if you just heat it up with the light, you can selectively first make the first product, and then you can really make the second product by 2+2 cycloaddition reaction. And interestingly, these two double bonds in the crystals, as I'll discuss, it is 5.9 angstrom. And technically, in this particular distance, you should not be able to get any reaction. But we got these particular reactions here. I'm going to discuss these things here. So the design was initially, it was not a plan. So we mixed these two particular components 1-to-1. We tried to grade the crystals. We did not know what kind of crystal we'll get. So these particular crystal will form, this is like a block shape big crystals is there. You can see this is like 2-to-1 ratio. So two dual benzenes are there, one BP is there. And this is the crystal structure. In the crystal structure, you can see that two double bonds are very far from each other, around like 5.9 angstrom. And technically, you should not get any reaction because the distance is very, very far. And we have checked the bulk crystallinity with the simulated pH study data. So it's matching with the bulk crystallinity. There is no other phase. Only one phase is there, means only one component is there. And this is the video I have. I don't know whether I can. Yeah, so this is the video I'm going to show here. You can see this is the crystal. Upon hitting the light, you can see it's forming the crack. You see it's forming the crack. And also it's moving very interesting. It's called a photosalient effect. So after a certain point, you can see it's completely broken. And then you just have to take the crystal out, dissolve in a solvent, and just put it in the NMR, and you will see the formation of the Huckel benzene. So in this case also, there is no indication that it will form 2+2 cycloaddition reaction. So then we look back the literature and see how things are actually known. So this particular complex is actually known. So this is benzene dicarboxylic acid with BPE. If you just mix 2-to-1 ratio, you'll get these kind of crystals. In this case, 2+2 cycloaddition reaction does not occur because this distance is very far. It's 4.9 angstrom. Then we also grow one more crystals where we have benzene, but we have tetramethyl group here. Because of the buttressing effect, two carboxylic acid groups are actually very close to each other. And we have a nice setup where the double bonds are actually very close to each other, 3.7 angstrom. And we have a nice like single crystal to single crystal reaction. You can just have to take the crystal, put it in the light source, and the same crystal, you just go back and measure it, you will see the formation of this cyclobutane ring here. Now the question is, if you take this crystal, what is going to happen? Will there be any 2+2 reaction or not? So we check the NMR by time-dependent study. We have seen that after 15 minutes of irradiation, we have 60% of Huckel benzene formation from here to here, and we have already started seeing the formation of the 2+2 reaction. And after 1 day of complete irradiation, we've seen that 86% of conversion is there for particular cyclobutane formation. And if you look at the kinetics, you can see that this duobenzene to huckel benzene formation is very efficient. It just forms within an hour. But in case of the other reaction, it takes like a day, right? So the quantum yield for the duobenzene to huckel benzene is almost like 15 or 16. But in this case, for the 2+2 cyclohydrogen reaction, it's almost like 0.3 to 0.4. And because of that, it's very, very slow. Now we need to understand why this reaction is happening. Although we have very long distance between the two double bonds, but we are seeing the formation of the product is a good amount. So why it is happening? So then we went back to the quantum mechanical calculation with the help of Professor Kane Houck. So you can see from the cartoon diagram, so these two green balls are actually far from each other. We postulated that once the huckel benzene is formed here, these two blue balls actually close to each other, and is actually forming the nice pattern to form the next reaction. So this is the calculated structure. In this calculated structure, you can see that two double bonds are actually very close to each other. It's 4.1 angstrom, and it should react. It is actually postulated that once you have the distance between the two double bonds at around 4.2 angstrom, it should react. And actually, these particular intermediate we have validated through PXRD. So this is the simulated PXRD from taking the CF of this particular compound. And this is the experimental data. You can see like the red stars actually the formation of the intermediate. So in that way, we have concluded that this intermediate is forming during the reaction time. And then finally, we can get the final product with 2+2 cyclohydrogen reaction. You can find the extensive results by looking at the paper. And at the end, I would like to just touch upon a little bit of the work that is just recently published, that how the electron matter interaction works. So far, I've discussed about the photochemistry, the light matter interaction, but how about the electron matter interaction? Is it possible to use the electron as a reagent? If it is so, then we don't have to use this light. We don't have to think about excited state and all. We just have to take the compound, put it in the system where the electron can heat the system, and then we can get like multiple reactions. So this is the recent work we have published, where we have shown that single electron can perform 90,000 reactions. So we have a bunch of compounds at the crystals. With the heat that we are heating the compound with the electrons, and then we are having the chain reactions, and we get like really 90,000 reactions per electron. By looking at this particular image, you can see at the beginning, we can see like a lot of diffraction. But after just a couple of seconds, you can see there is no diffraction. It's just from the product. It's very, very efficient, very, very fast. So pictorially, you can see we have a lot of starting material. We are using the electron in inelastic scattering. So it just heats the molecule that takes the electrons out, and it forms a radical cation. Once a radical cation will form, it forms the radical cation product. And these radical cation product take the electron from the next R to form the product, quenched product, and excited radical cation. In that way, you have a lot of reaction in the system. So we have an X-ray structure for the starting material. That starting material is actually duobenzene, and two adamantyl groups are there. This is actually used for rigidify the system. And by looking at the extensive packing with this duobenzene, you can see that this is one duobenzene, this is one duobenzene, this one. So it's like a zigzag where you have the duobenzene very close to each other. So once you start the reaction with the one duobenzene, it can just proliferate to the other duobenzene to form the extensive reaction. And this particular product, we have also X-ray structure from the cryo-electron microscope. So in this case, we have taken the duobenzene mechanistically. We just heat the molecule with the electron to form the radical cation. This radical cation will form the huckel benzene radical cation, and that huckel benzene radical cation take the electron from the next duobenzene to form the benzene and another duobenzene radical cation. This is the energetics. You can see like this is the starting material, this is the radical cation. Now the product radical cation is there. Now this product radical cation take the electron from next starting material, and it gets excited to the again duobenzene radical cation, and in that way you have a complete chain reactions. So in that way we can say like we have like huge amount of reaction by the electron. We are trying to investigate these days to like find out more reactions where we can just introduce electron as a single reagent to perform the reaction. So in that way, I would like to summarize. So first, I talked about the duobenzene that has been sensitized with benzophenone, where in solid we have quantum yield around 120, and in polycrystalline suspension we have quantum yield around like 300. And then I have talked about the mixed crystal approach, where there is no sensitizer, but we can really amplify the quantum chain here. And then I talked about the cascade reaction in the crystals, where one reaction is actually facilitating the next reaction, although we have a distance problem. So the first reaction is actually accelerating the second moiety to come close to each other, and then we have a second reaction. And then the third one is actually touch upon a little bit of the electron-induced reaction in the crystals. So this is the first example that we published. We're trying to investigate more on it. So we found recently a couple of more examples where we can really see like even millions of reactions per electrons. So this is really amazing to see these kind of reactions with electrons. So I mean, you don't need to use kind of like a standard setup for doing this reaction. Even you can do this reaction in SCM. You just put the sample in the SCM, hit with the electrons, and take the sample out and dissolve in NMR solvent and check the reaction profile. So the problem for this particular set of reaction is like we cannot do this kind of reaction in gram scale. We can just do this kind of reaction in milligram scale. So we are just trying to figure out how we can like set up a proper system where we can use reaction in the gram scale. So at the end, I would like to first of all thank Professor Y.D. Vankasa from IIT Kanpur. So he's the one first to give me the chance to work in his group, and I mean he was a great mentor, and I learned a lot of things from him. And his group was also amazing. I could see Resmiti is still here. The Parasuramon was like a great person. So it was like a nice memory in his group. Thank you so much, sir. I can see you are in the guest. And by taking his help, I got a chance to do PhD, Professor Michael Smittel's lab, and then I spent there to do like molecular machine. And then currently I'm working with Professor Miguel Garcia Garibay. So he's such a nice mentor. So I'm still learning a lot of things from him. And I would like to also thank Signature Discovery as a company that I spent like 1 year. I really learned a lot of things from there, like particularly in the synthetic perspective. And then at the end, I would like to also thank a lot of funding agencies like IIT Kanpur, University of Jigen, DFG, UCLA, and NSF. And also, I'd like to thank MITS for giving me the chance for this talk. Thank you so much, and I would like to have more questions, suggestions, or comments if you have. Thank you so much.
Thank you, Dr. Indrajit, for a nice presentation. So the session is open for discussion. Participants can come up with their questions.
Hi, Indrajit, this is Supriya here. Fascinating talk. I have quick naive question, two naive questions. One is that the electron mediated reaction you showed, right? So it's like a strain system, right? So somehow you release the strain, and that's what you find many reactions at a time, right?
Right.
So I think due to the strain. So do you study other kind of reaction like where you have less strain and with a similar reaction and see that similar efficiency can be obtained or not?
Yeah, that's a good question. Actually, we have other examples that I'm not going to flash here because I'm not allowed to. Actually, some systems there are no strain. Also, we are trying to do the reaction with electrons. We found there actually even much higher than 90,000 reactions there. So yeah, we have some examples.
Mm-hmm. And in the slide 29, bottom left, previous slide, yeah. So when this 2+2 cyclization happened, right? So you mentioned, is there any changes you find and how you monitor the reaction? Like you change any crystal pattern or shape of the crystal or color or something? How you monitor
in this case, actually, we studied through PXRD. We studied actually through single crystal to single crystal. The problem is, once you start doing the reaction, it's actually changing the phase. We cannot do any single crystal to single crystal study. But once you do the reaction, you can really see the change of the color. So, I mean, initially it was like colorless crystals. So after doing the reaction, it turns a little bit brown. But from the PXRD, you can see like nice patterns are there. So you can really see like intermediate like this.
Mm-hmm. Okay, thank you.
Yeah, Dr. Vankar, kindly.
Yeah. Can you hear me?
Yes, I can hear you, sir.
Okay. Indrajit, very nice to see you and listen to your talk. Very nice talk.
Yeah, thank you so much, sir. Nice to hear you also.
Yeah, but you have moved out completely from what you did your PhD and postdoc and other places.
Yes.
Yeah, very nice. The only thing that I would like to know is when you said you are doing this reaction. So first of all, the same question I had as Professor Day, Dr. Day asked. That basically it is the strain system that and it goes to aromatized molecule. That is what you showed. And also you did on a small scale. So small scale from few milligram is how many milligrams? Like what is the maximum number of milligrams that you have taken such reactions?
So this is for the photolysis reaction or electron-induced reaction?
Both of them. I mean.
So for the photolysis reaction, we have performed even in gram scale. So we have performed 40 gram scale reactions. So for that, you cannot just do the normal photolysis. You just have to use a setup where the light should be immersed into the solvent. Like solvent means in the suspension. You have to put the light inside the suspension, then only you can get the quantum chain reaction. Because once you have like a milky suspension, light cannot penetrate. So in that way, you can even like we have done reaction like 1 gram to 40 gram scale. But in case of electron-induced reaction, so far we have used like few milligrams. So we don't have like a setup to introduce.
How many 3 milligrams?
It's like 1 to 5 milligrams.
Oh, that's too low.
Yeah, because we don't have a right setup to introduce these electrons because we are using cryo microscope. In the cryo electron microscope, we have like very tiny like a sample holder, so that we can put like only 0.1 milligram to 5 milligram around.
Okay. Yeah, I just hope that you are in a position to expand the scope of this electron based reactions so that on large scale and also to many other substrates.
Yes, we are trying to look at that.
Okay, thank you.
Yeah, thank you, sir.
Yeah, no more questions from participants, I think. So thank you, Dr. Indrajit, once again for your nice presentation. And
definitely, thank you so much for the invitation. I also need to leave from this session because it's a late night. I need to go home.
I understand. So
yeah, it's almost 10 o'clock in US.
Yeah, thank you. Yeah. So
thank you so much for the invitation.